So let me remind you what we figured out on the previous slide there. We figured out that our general AN, well, we figured out A0, first of all, was equal to 3. We got that on the previous slide. Our general AN is 2/3 times the integral from 0 to 3 of 3 minus x times cosine of n pi x over 3 dx. And I want to integrate that, but that's going to require integration by parts. So I'm going to set up my tabular integration here, 3 minus x, and cosine of n pi x over 3. So I take derivatives of 3 minus x. So that's the derivative of 3 minus x is -1, and the derivative of -1 is 0. And then I take integrals of cosine of n pi x over 3. So the first integral is sine of n pi x over 3. And I multiply that by 3 over n pi by the chain rule. Now the integral of sine is negative cosine n pi x over 3. And I multiply that by another 3 over n pi. So 9 over n squared pi squared. That got a little bit squished in there. Let me rewrite that. 9 over n squared pi squared. And then I do plus and minus. So I'm going to multiply down those diagonals there. And so what I get is 2/3. Now, fairly complicated here. 3 minus x times 3 over n pi times sine of n pi x over 3. n pi x over 3. I see 3 negatives here. Negative, negative, negative. So it's the whole thing is negative. Minus 9 over n squared pi squared. Cosine of n pi x over 3. And I'm supposed to evaluate that whole thing from x equals 0 to x equals 3. So, nice thing here is I see I've got this complicated expression right here, but if I plug in x equals 3 or x equals 0 into this, I'll get a whole multiple of n pi inside the sign. Excuse me. So, that term's going to go to 0 on both sides there for x equals 3 or for x equals 0. So that's really nice. On the other side, it's not so good. So I still got 2/3. Now, for the cosine term, minus 9 over n squared pi squared times cosine of n pi 3 over 3, so just cosine of n pi, plus 9 over n squared pi squared, times cosine of 0, which is just 1. So let me close that off. I think I'm going to factor out the 9 over n squared pi squared, and 2/3 of that would give me 6 over n squared pi squared. And then I've got 1 here, and minus cosine of n pi. And let's remember that cosine of n pi, we worked this out earlier, cosine of n pi is, well, when n is even, then cosine of n pi is 1. And when n is odd, cosine of n pi is -1. So if n is even, then cosine of n pi is just going to be 1. So we get 1 minus 1, so it's 0. So this is 0 if n is even. And if n is odd, then cosine of n pi is -1. So we get 1 minus -1, which is 2. So 12 over n squared pi squared if n is odd. So that's my my expression for a sub n. It's 0 if n is even, and it's 12 over n squared pi squared if n is odd. So now let me remind you of the generic form for Fourier series of x. For the Fourier series of a function, it's a0 over 2 plus the sum from n equals 1 to infinity of an cosine of n pi x over L plus bn sine of n pi x over L. Now for this one, we already arranged the function so that all the signs dropped out because we made the function be even. So I don't need to worry about the signs. All of those dropped out. But I do still have all these cosine terms. So let me fill in what I have for the cosine terms. A naught, that's up there. A naught over 2 is 3/2. Plus, now let's see what we get for n equals 1. That's an odd one, so I get 12 over pi squared cosine of 1 pi x over 3, so pi x over 3. N equals 2 is even, so I have a 0 there. Put a 0 there. N equals 3, it's an odd one, so 12 over 9 pi squared, n squared pi squared, times cosine of 3 pi x over 3. I'll just go ahead and write it out that way so it's easier to see the pattern. 3 pi x over 3. N equals 4 is even, that was 0. N equals 5 is 12 over n squared pi squared, so 25 pi squared, cosine of 5 pi x over 3. I'm out of space here, so I'm not going to write any more there. But I see that I've got a certain pattern here of odd terms, so I'm going to try to combine those and maybe make a new series. Here's how I can keep track of odd terms. I can start at n equals 0 and just use 2n plus 1 to keep track of all the odd numbers that I see. So I think I can factor out 12 over pi squared from everything there. And then on the denominator, I'll have an odd number squared. So 1 over 2n plus 1 squared times cosine of an odd number, so 2n plus 1, times pi x all over 3. And that's the last word on my Fourier series using only cosines for that function. So let me recap everything we did there. We figured out that a0 is equal to 3. That was on the previous slide, so not doing that again. The an, we got this formula on the previous slide for my ans, and of course that's an integration by parts problem. So I went to my integration by parts table here. This is tabular integration by parts. And I worked out derivatives of 3 minus x, integrals of cosine of n pi x over 3, and I connected them up with little diagonal lines with alternating signs. Put it all together and got this pretty horrible expression for the integral. But the nice thing is that the sine term, whether you plug in x equals 3 or x equals 0, it's going to go to 0. The cosine term is not so good. If you plug in x equals 3, you get cosine of n pi. So this is x equals 3. And if you plug in x equals 0, you get cosine of 0, which is 1. But it's being subtracted. It's minus, but it's also the lower limit. So we get 2 minuses canceled to give us a plus there. So we have 2/3 times, it looks like I factored out the 9. 9 times 2/3 is 6. And then I factored out the n squared pi squared. So the 9 and the 2/3 gave you the 6 there. And the n squared pi squared came out. But we still had a 1 here and a cosine minus cosine of n pi. And cosine of n pi, we figured this out before, is if n is even, it's 1. If n is odd, it's -1. And so when n is even, we just have 1 minus 1, so it gives us 0. If n is odd, we have 1 minus -1. So that would be 1 minus -1. Let me write that properly. If n is odd, we have 1 minus negative 1, so we get 2, and 2 times 6 over n squared pi squared gives us 12 over n squared pi squared. So that's our coefficient an, kind of complicated. Sometimes it's 0, sometimes it's 12 over n squared pi squared. And then I remembered my general Fourier series formula, a naught over 2 plus an times a cosine term, bn times a sine term. And we remembered that for this particular one, we had extended the function to be even. It's an even function, which means that all the bn's are 0, so there's no sine terms. We did that deliberately because the problem asked us to find a function that had all cosines. And so my a naught was 3, that came from up here. And my an's, I dropped in the 12 over n squared pi squared. There's the odd ones right there, and then we dropped in 0 for the even ones. And then I tried to rewrite this because I noticed that I had exactly the odd terms. Well, the 3 halves is kind of a special case. But I see I have all the odd terms here. 1, 3 squared, 5 squared. So to find a new pattern for odd terms, I used 2n plus 1 generates odd numbers. So I factored out the 12 over pi squared from all of them. All of them have 1 over 1, 1 over 9, 1 over 25. So I wrote that as 1 over 2n plus 1 squared. And then in the numerators, there's 1 pi x, 3 pi x, 5 pi x. So that's 2n plus 1 pi x over 3. So that gives me a Fourier series for that function using only cosines, which is what we were asked to do. So that wraps up this lecture on Fourier series. This is part of the Differential Equations lecture series on Educator.com. What we're doing here is we're trying to solve partial differential equations, although we didn't really get a chance to look at them in this lecture. We just had to do a lot of background on Fourier series. But the whole point of that is that we're going to use Fourier series to solve partial differential equations. So we're going to learn about that in the next lecture, where we find the solution to the heat equation. So I hope you'll stick around and watch the next lecture, which is on using Fourier series to solve the heat equation, and that'll wrap up our set of lectures on partial differential equations. So once again, you're watching the lectures on differential equations here on Educator.com, and my name is Will Murray, and I thank you very much for joining us today. Bye-bye.